Section 13 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 13. The Abolition of Force. In the Newtonian system, bodies under the action of no forces move in straight lines with uniform velocity. When bodies do not move in this way, their change of motion is ascribed to a force. Some forces seem intelligible to our imagination. Those exerted by a rope or a string, by bodies colliding, or by any kind of obvious pushing or pulling. As explained in an earlier chapter, our apparent imaginative understanding of these processes is quite fallacious. All that it really means is that past experience enables us to foresee, more or less, what is going to happen without the need of mathematical calculations. But the forces involved in gravitation and in the less familiar forms of electrical action do not seem in this way natural to our imagination. It seems odd that the earth can float in the void. The natural thing is to suppose that it must fall. That is why it has to be supported on an elephant, and the elephant on a tortoise, according to some early speculators. The Newtonian theory, in addition to action at a distance, introduced two other imaginative novelties. The first was that gravitation is not always and essentially directed what we should call downwards, i.e., towards the center of the earth. The second was that a body going round and round in a circle with uniform velocity is not moving uniformly in the sense in which that phrase is applied to the motion of bodies under no forces, but is perpetually being turned out of the straight course towards the center of the circle, which requires a force pulling it in that direction. Hence Newton arrived at the view that the planets are attracted to the sun by a force, which is called gravitation. This whole point of view, as we have seen, is superseded by relativity. There are no longer such things as straight lines in the old geometrical sense. There are straightest lines, or geodesics, but these involve time as well as space. A light ray passing through the solar system does not describe the same orbit as a comet from a geometrical point of view. Nevertheless, each moves in a geodesic. The whole imaginative picture is changed. A poet might say that water runs downhill because it is attracted to the sea, but a physicist or an ordinary mortal would say that it moves as it does at each point because of the nature of the ground at that point, without regard to what lies ahead of it. Just as the sea does not cause the water to run towards it, so the sun does not cause the planets to move round it. The planets move round the sun because that is the easiest thing to do, in the technical sense of least action. It is the easiest thing to do because of the nature of the region in which they are, not because of an influence emanating from the sun. The supposed necessity of attributing gravitation to a force attracting the planets towards the sun has arisen from the determination to preserve Euclidean geometry at all costs. If we suppose that our space is Euclidean, when in fact it is not, we shall have to call in physics to rectify the errors of our geometry. We shall find bodies not moving in what we insist upon regarding as straight lines, and we shall demand a cause for this behavior. Eddington has stated this matter with admirable lucidity. He supposes a physicist who has assumed the formula for interval which is used in the special theory of relativity, a formula which still supposes that the observer's space is Euclidean. He continues, "Since intervals can be compared by experimental methods, he ought soon to discover that his formula for the interval cannot be reconciled with observational results, and so realize his mistake. But the mind does not so readily get rid of an obsession. It is more likely that our observer will continue in his opinion, and attribute the discrepancy of the observations to some influence which is present and affects the behavior of his test bodies. He will, so to speak, introduce a supernatural agency which he can blame for the consequences of his mistake. The name given to any agency which causes deviation from uniform motion in a straight line is force, according to the Newtonian definition of force. Hence the agency invoked through our observer's mistake is described as a field of force. A field of force represents the discrepancy between the natural geometry of a coordinate system and the abstract geometry arbitrarily ascribed to it. If people were to learn to conceive the world in a new way, without the old notion of force, it would alter not only their physical imagination, but probably also their morals and politics. The latter effect would be quite illogical, but is none the less probable on that account. In Newton's theory of the solar system, the sun seems like a monarch whose behests the planets have to obey. In Einstein's world there is more individualism and less government than in Newton's. There is also far less hustle. We have seen that laziness is the fundamental law of Einstein's universe. The word dynamic has come to mean, in newspaper language, energetic and forceful. But if it meant illustrating the principles of dynamics, it ought to be applied to the people in hot climates who sit under banana trees waiting for the fruit to drop into their mouths. I hope that journalists, in future, when they speak of a dynamic personality, will mean a person who does what is least trouble at the moment, without thinking of remote consequences. If I can contribute to this result, I shall not have written in vain. It has been customary for people to draw arguments from the laws of nature as to what we ought to do. Such arguments seem to me a mistake. To imitate nature may be merely slavish. But if nature, as portrayed by Einstein, is to be our model, it would seem that the anarchists will have the best of the argument. The physical universe is orderly, not because there is a central government, but because every body minds its own business. No two particles of matter ever come into contact. When they get too close, they both move off. If a man were had up for knocking another man down, he would be scientifically correct in pleading that he had never touched him. What happened was that there was a hill in space-time in the region of the other man's nose, and it fell down the hill. The abolition of force seems to be connected with the substitution of sight for touch as the source of physical ideas, as explained in Chapter 1. When an image in a looking-glass moves, we do not think that something has pushed it. In places where there are two large mirrors opposite to each other, you may see innumerable reflections of the same object. Suppose a gentleman in a top hat is standing between the mirrors. There may be 20 or 30 top hats in the reflections. Suppose now somebody comes and knocks off the gentleman's hat with a stick. All the other 20 or 30 top hats will tumble down at the same moment. We think that force is needed to knock off the real top hat, but we think that the remaining 20 or 30 tumble off, so to speak, of themselves, or out of a mere passion for imitation. Let us try to think out this matter a little more seriously. Obviously, something happens when an image in a looking-glass moves. From the point of view of sight, the event seems just as real as if it were not in a mirror. But nothing has happened from the point of view of touch or hearing. When the real top hat falls, it makes a noise. The 20 or 30 reflections fall without a sound. If it falls on your toe, you feel it. But we believe that the 20 or 30 people in the mirrors feel nothing, though top hats fall on their toes too. But all this is equally true of the astronomical world. It makes no noise, because sound cannot travel across a vacuum. So far as we know, it causes no feelings, because there is no one on the spot to feel it. The astronomical world, therefore, seems hardly more real or solid than the world in the looking-glass, and has just as little need of force to make it move. The reader may feel that I am indulging in idle sophistry. After all, he may say, the image in the mirror is the reflection of something solid, and the top hat in the mirror only falls off because of the force applied to the real top hat. The top hat in the mirror cannot indulge in behavior of its own, it has to copy the real one. This shows how different the image is from the sun and the planets, because they are not obliged to be perpetually imitating a prototype. So you had better give up pretending that an image is just as real as one of the heavenly bodies. There is, of course, some truth in this. The point is to discover exactly what truth. In the first place, images are not imaginary. When you see an image, certain perfectly real light waves reach your eye, and if you hang a cloth over the mirror, these light waves cease to exist. There is, however, a purely optical difference between an image and a real thing. The optical difference is bound up with this question of imitation. When you hang a cloth over the mirror, it makes no difference to the real object, but when you move the real object away, the image vanishes also. This makes us say that the light rays which make the image are only reflected at the surface of the mirror, and do not really come from a point behind it, but from the real object. We have here an example of a general principle of great importance. Most of the events in the world are not isolated occurrences, but members of groups of more or less similar events, which are such that each group is connected in an assignable manner with a certain small region of space-time. This is the case with the light rays which make us see both the object and its reflection in the mirror. They all emanate from the object as a center. If you put an opaque globe round the object at a certain distance, the object and its reflection are invisible at any point outside the globe. We have seen that gravitation, although no longer regarded as an action at a distance, is still connected with a center. There is, so to speak, a hill symmetrically arranged about its summit, and the summit is the place where we conceive the body to be, which is connected with the gravitational field we are considering. For simplicity, common sense lumps together all the events which form one group in the above sense. When two people see the same object, two different events occur, but they are events belonging to one group and connected with the same center. Just the same applies when two people, as we say, hear the same noise. And so the reflection in a mirror is less real than the object reflected, even from an optical point of view, because light rays do not spread in all directions from the place where the image seems to be, but only in directions in front of the mirror, and only so long as the object reflected remains in position. This illustrates the usefulness of grouping connective events about a center in the way we have been considering. When we examine the changes in such a group of objects, we find that they are of two kinds. There are those which affect only some member of the group, and those which make connected alterations in all the members of the group. If you put a candle in front of a mirror, and then hang black cloth over the mirror, you alter only the reflection of the candle as seen from various places. If you shut your eyes, you alter its appearance to you, but not its appearance elsewhere. If you put a red globe round it at a distance of a foot, you alter its appearance at any distance greater than a foot, but not at any distance less than a foot. In all these cases, you do not regard the candle itself as having changed. In fact, in all of them, you find that there are groups of changes connected with a different center or with a number of different centers. When you shut your eyes, for instance, your eyes, not the candle, look different to any other observer. The center of the changes that occur is in your eyes. But when you blow out the candle, its appearance everywhere is changed. In this case, you say that the changes happen to the candle. The changes that happen to an object are those that affect the whole group of events which center about the object. All this is only an interpretation of common sense, and an attempt to explain what we mean by saying that the image of the candle in the mirror is less real than the candle. There is no connected group of events situated all round the place where the image seems to be, and changes in the image center about the candle, not about a point behind the mirror. This gives a perfectly verifiable meaning to the statement that the image is only a reflection, and at the same time it enables us to regard the heavenly bodies, although we can only see and not touch them, as more real than an image in a looking-glass. We can now begin to interpret the common sense notion of one body having an effect upon another, which we must do if we are really to understand what is meant by the abolition of force. Suppose you come into a dark room and switch on the electric light. The appearance of everything in the room is changed. Since everything in the room is visible because it reflects the electric light, this case is really analogous to that of the image in the mirror. The electric light is the center from which all the changes emanate. In this case, the effect is explained by what we have already said. The more important case is when the effect is a movement. Suppose you let loose a tiger in the middle of a bank holiday crowd. They would all move, and the tiger would be the center of their various movements. A person who could see the people, but not the tiger, would infer that there was something repulsive at that point. We say in this case that the tiger has an effect upon the people, and we might describe the tiger's action upon them as the nature of a repulsive force. We know, however, that they fly because of something which happens to them, not merely because the tiger is where he is. They fly because they can see and hear him, that is to say, because certain waves reach their eyes and ears. If these waves could be made to reach them without there being any tiger, they would fly just as fast, because the neighborhood would seem to them just as unpleasant. Let us now apply similar considerations to the sun's gravitation. The force exerted by the sun only differs from that exerted by the tiger in being attractive instead of repulsive. Instead of acting through waves of light or sound, the sun acquires its apparent power through the fact that there are modifications of space-time all round the sun. Like the noise of the tiger, they are more intense near their source. As we travel away, they grow less and less. To say that the sun causes these modifications of space-time is to add nothing to our knowledge. What we know is that the modifications proceed according to a certain rule, and that they are grouped symmetrically about the sun as center. The language of cause and effect adds only a number of quite irrelevant imaginings, connected with will, muscular tension, and such matters. What we can more or less ascertain is merely the formula according to which space-time is modified by the presence of gravitating matter. More correctly, we can ascertain what kind of space-time is the presence of gravitating matter. When space-time is not accurately Euclidean in a certain region, but has a non-Euclidean character which grows more and more marked as we approach a certain center, and when, further, the departure from Euclid obeys a certain law, we describe this state of affairs briefly by saying that there is gravitating matter at the center. But this is only a compendious account of what we know. What we know is about the places where the gravitating matter is not about the place where it is. The language of cause and effect, of which force is a particular case, is thus merely a convenient shorthand for certain purposes. It does not represent anything that is genuinely to be found in the physical world. And how about matter? Is matter also no more than a convenient shorthand? This question, however, being a large one, demands a separate chapter. End of section 13.